Hello everyone, this is lecture 13, vectors in Rn, or this is n-dimensional vectors. So in this lecture, we're going to kind of formally introduce the notions of vectors and the components of a vector. We're also gonna do some manipulations on vectors, or we're gonna learn how to perform some basic vector operations, such as scalar multiplications, vector addition, vector subtractions, right? And we're going to do this in component forms. And of course, and at the end of the lecture, we're going to briefly talk about something called linear combinations of vectors, which is a very important concept in linear algebra. And we're going to explore this concept, the concept of linear combinations of vectors later on in the course as well. All right, so let me give you definitions for scalars and then vectors. And then we're gonna do things related to vector in this particular lecture. All right, so for scalars, probably some of you have heard about scalar and vector in physics courses and even in calculus. So scalar is just some physical quantity that have only magnitude, whereas vectors are a physical quantity that have both magnitude or length and directions, right? So when you talk about vectors, for example, velocity of a car, you need to give the magnitude of the velocity, that means the speed, and also the directions in which the velocity is heading to. All right, so that's kind of the definitions of scalars and vectors. So let me write down the definitions of scalars. Are the physical quantity that have only magnitude. The example for scalar, you can have many examples. So distance, when you talk about distance, that's the scalar, right? Or temperature. Or you talk about mass or weight, so things like that. And when you talk about vectors, also physical quantity that have both direction, magnitude, and directions. Some of the common example that you guys usually see for vectors are velocity, accelerations, force, momentum, things like that. So velocity, accelerations, force, momentum. All right. So the notations for a vector, right, in linear algebra, in mathematics in general, and in physics or any sciences for that matter, is denoted as you have a bold letter, and on top of that you have an arrow, right, to indicate kind of the directions that the vector is going. Right? So in this case, it's just a bold letter, right? If you zoom in here, it's just a bold letter. But when you actually write on a piece of paper, and when you do work, you kind of cannot really write a bold letter. So we use an arrow on top of a letter to indicate vectors. Right? So in this case, you use vector V, right? Right. And the vector consists of 2 points, right? This is point A and this is point B, and point A is called the initial point, right? Or it's called a tail. Right. And usually by conventions, the vector, the initial point start at the origin, but not always, right? It's easy to consider a vector when the initial point start at the origins. Yeah. So B is called the terminal point. Or we call it the head. All right. So in this case, this is vector v, but this is also can be written as a b vector, right? So this indicate that this vector is going from A to B, right? So the arrow pointing the direction in which the vector is going. It's going from point A to point B. Okay. And if you consider the two-dimensional cases on the plane, the xy plane, you have a vector of two components, right? X component, y component, or x1 component and x2 component. So in the case of two-dimensional vector, right? So 2D vector mean two-dimensional vector is of the form x1, x2, right? Or x comma y, doesn't really matter. So x1, x2 are called the components of the vector, component of vector. All right. In the case of three dimensions, three-dimensional vector, you have three components for the vector x1, x2, and x3, right? And again, x1, x2, and x3 are the components of the vector. Right, so it's very straightforward. Hopefully, later on we will rewrite this two-dimensional vector, three-dimensional vectors, and also we're going to define the n-dimensional vectors. Right, so the next definition is equivalent vectors. So vectors with the same length and directions are called equivalent vector. All right, so you have four different arrows here, and I'm going to indicate this is v1, vector v1, this is vector v2, this is vector v3, and this is vector v4. And these four vectors are equivalent vectors because they have the same length, and pointing in the same directions. So the vectors on the left are equivalent vectors. And so you say that v1 equal to v2 equal to v3 equal to v4. Right. If you consider two different vectors, so the vectors u with the component u1, u2, and another vector v equal to v1, v2, we say that these two vectors are equal, right? If and only if the components are equal to one another, right? The corresponding components, that means u1 equal to v1 and u2 equal to v2. So that this is the definitions of equivalent vectors, or the vectors with the same length or directions, right? So they are equal to one another if the corresponding components are equal to one another. That is u1 equal to v1, or the first component equal to one another, and the second component equal to one another. Okay. To sketch a vector on the xy plane is very straightforward, just like you plot points on an xy plane. You just plot 2 points, right? So the first point is a equal to -1, 2, and the second point is b equal to 3, 4, just like you plot regular points. But the additional step is that you connect these 2 points together and draw an arrow in the particular directions. So in this case, you know that the initial point is A, so and the terminal point is B. So the arrow is going to be at B. So the point is -1, 2. So this is the point. So this is point A. And the second point is 3, 4. So 3, 4, this is the point. And you're going to connect these 2 points together. And the arrow is at the terminal point. So this is the vector that you have. All right. You can do translations for vectors. That means translation means you move the point to the right. You move the vector to the right. You move the vector to the left. You move it up, you move it down, doesn't matter where you want to do. Later on, we're gonna do something related to scaling vector, right? You can scale it up, you can scale it down, right? Things like that. Again, by convention, at the beginning, when you talk about initial point and terminal point, usually when you talk about a vector, right, the initial point is at the origin. Here, clearly, the initial point is not at the origin, but you can actually transform this or do translations to move this initial point back to the origin. And when you do that, you need to move the entire vector back to the origin. Right, so move it here, and this is the terminal point. Now you have the vector starting at the origins. So this particular concept is called translations. You move it to the right, you move it down, you move it up, you move it to the left, and things like that. All right, so the next operations, next thing we're going to consider the vector operations. Right? There are two basic operations that we can use or we can perform on vectors. The first one is the vector addition, and the second one is scalar multiplications. Right? And the vector subtraction is actually related to vector additions, and we'll see that in a few minutes. Right? But first, you can perform vector additions on vectors. So to add two vectors in the plane. Right, so when we talk about plane, an XY plane, or this is just the two-dimensional case, R2, what you do is you add their corresponding component. Right, so if you have two vector u and v, vector u consists of u1, u2, and vector v consists of v1, v2. When you want to add these two vectors together, what you do is the first component get added together, and the second component get added together. That's how you perform vector additions on these two vectors. All right, so let's quickly do the following example. So I want to do vector additions on the two vector u and v, given u is equal to 1/4 and v equal to 2, -2 in this case. So I have u plus v equal to 1/4 plus 2, -2. Well, this is 1 plus 2, 4 minus 2. Well, this is 3, 2. Right? So you have a new vector, and this new vector consists of two components, 3, 2. All right. So this is the plot of the vector additions that you see here. Right? So graphically, this is the vector 1, 4. Right? 1, 4. This is vector u, and this is vector v. When you perform vector addition, you obtain a new vector called 3, 2. And this is the new vector that you just obtained. Right? So the next example, you have u equal to 3, -2, and v equal to -3, 2. So u plus v is equal to 3, -2 plus -3, 2, or 3 plus -3, -2 plus 2, and you obtain the 0 vector. Right? Graphically, this is what you see. You have vector u in this particular direction, and vector v is directly in the opposite direction of u. So that's why when they add together, they kind of cancel out the component, cancel out, and you get the 0 vector, which is the origins right here. All right. And the last example, you have the vector u equal to 2, 1, and the vector v is 0, 0. So v in this case, the 0 vector. So u plus v is equal to 2, 1 plus 0, 0. Well, this is 2 plus 0, comma 1 plus 0. So you obtain 2, comma 1. So this is the you add the 0 vector, and then it just the is equal to the vector, the non-zero vector that you do the addition with. Okay, so this is vector u, right? And vector v is just the 0 vector. So the sum u plus v is actually equal to the vector u. All right, so that is the vector additions. Now we move on to a second operation, is scalar multiplications. So to multiply a vector v by a scalar c, what you do is you multiply each of the components of v by c, right? So that is, you have c times v is equal to c times v1 comma v2, or this is equal to c times v1 comma c times v2. So c is a scalar. Another word for scalar in this particular case, it's just some real numbers, some real constant, right? And the value of c doesn't matter because c in this case is going to be a scale for your vector, right? So you can scale it up, you can scale it down. You can make the vector longer, or you can make the vector shorter, right? And also the sign of the sign of c matters as well, because if c is positive, the constant multiple c times v is going to be in the same direction as the original vector v. If c is negative, then the constant multiple of c times v is going to be in the opposite directions of the original vector v. Okay, so let's write that down. So when c is positive, c times v has the same direction as the vector v, right? And when c is less than 0, c times v has the opposite direction as v, right? So, which is a very important concept, right? So be careful when you have a constant multiple. Sometimes c can be positive, sometimes c can be negative. If c is equal to 0, you scale the original vector back to the origins. Okay. Now the product of a vector v and the scalar -1 is denoted by so -1 times vector v give me negative v, right? So this is the negative of v. Okay, and therefore, so with this kind of definitions is not really defined earlier. So this is the first time you see a negative of a vector, right? It's just that you have the original vector v. The negative v means that you turn the original vector into the opposite directions. They have the opposite directions, but they have the same length. Okay, so the difference, now we want to do vector subtraction, or the difference of two vectors. So the difference of u and v is that of u minus v equal to u plus negative v, right? So instead of doing subtraction, you actually perform a vector addition. You just add a negative of a vector, right? So here a quick note that vector v is subtracted from u by adding the negative of v. All right, so that's the concept of vector subtractions or difference between two vectors. Instead of doing actual subtraction, you actually add in the negative of the vector. So let's do in the following calculations. So you have two vectors, u and v again. In this case, u is equal to 3, 4, and v is equal to -2, 5. So I'm going to do some scaling for vector v. So you scale it down because you multiply v by 1/2. So you scale the vector down a little bit, make this vector smaller, but still in the same directions as v. So 1/2 times -2, 5, or this is equal to -2 over 2, 5 over 2, or is equal to -1, 5 over 2. So now for the second part, u minus v, that is 3, 4 minus -2, 5. So what you do is you do 3 minus -2 and a 4 minus 5, and you get the answer to be 5, -1. So you will form the calculation similar to when you do the vector additions. Now, the last part here is 1/2 v. Right? So we have the 1/2 v already. So it's going to be -1, 5 over 2 added with 3, 4. Right? Well, this is -1 plus 3, 5 over 2 plus 4. Or this is the vector 2, 13 over 2. All right. So if you have a vector, usually you are given a component, u1, u2, or v1, v2 for that matter. But if you just have the initial point and a terminal point, how would you find the component of the vector? So the next definition give you a formula to do so. All right, so component form of a vector. So let a v be a vector with initial point x1, y1, and a terminal point x2, y2. Then the vector v can be expressed in component form as. So the vector v is going to be equal to x2 minus x1, right? The first component of the terminal point minus the first component of the initial point, and y2 minus y1, so the second component of the terminal point minus the first component of the initial point. So in this case, again, you see this is the two-dimensional vector, and two-dimensional vector has the form v1, v2, and in this case, you have three-dimensional vectors. You have v is equal to v1, v2, v3, and in this case, on the xy plane, you have 2 points. The initial point is x1, y1, and the terminal point is x2, y2. So why do I know this is the terminal point? Because the arrow is at the point. Right? So therefore, what you can do to calculate v or p1, p2, vector p1, p2, is that you're going to do x2 minus x1, y2 minus y1. All right. So here in the following example, you want to calculate the vector v. Vector v is equal to p1, p2, vector p1, p2, because the initial point is p1 equal to 2, -1, 4, and the terminal point p2 is 7, 5, and -8. So you get v equal to p1, p2 equal to 7 minus 2, 5 minus -1, comma -8 minus 4. And you get the vector consists of the following component: 5, 6, -12. Okay. So far up to this point, we do example, we talk about vectors in 2 dimensions, and we actually perform calculations on vector in 3 dimensions. We actually can perform this type of calculations or perform these operations on vectors with n components or n-dimensional vectors, or any vector of any size for that matter. So here's kind of the definitions for vectors in Rn. Right, so if you have just R1, which is the regular real numbers, we call this one space. Is the set of all real numbers. Right. Usually you have a straight line, the real number line, right? So that's R1. So when you talk about R2, that's the XY plane, right? 2-dimensional case or 2-dimensional vector that you can perform, you can play with. So this is set of all order pair of real numbers. Right. So usually here, 2-dimensional vectors written as, for example, v is equal to v1, v2. Right. Now moving on to the case of 3-dimensional, right? So the x, y, and z plane space, sorry, 3 space. So R3, so 3 space. This is the set of all order triples of real numbers. And for 3-dimensional vectors, it's going to be of the form v1, v2, v3. Again, v1, v2, v3 are the components of the vector. You can do the same for 4 dimensions, 5 dimensions, or 4 space, 5 space, and so on and so forth. But in general, what you can do is you can do Rn, which is n space, which is the set of all order n tuples of real numbers. Right. So n-dimensional vector has the form v. So it has n component, and usually the notation is that we just do v1, v2, and we're going to use ... to indicate there's a bunch of them, of component in between v1, v2, and vn. Okay, so that's n-dimensional vectors. And you can perform the same calculations or operations on the n-dimensional vector, right? So you can do vector additions and scalar multiplications on n-dimensional vectors. All right, so let u equal to u1, u2 up to un, and v equal to v1, v2 up to vn. Be vectors in Rn, right? And let C be a real number. So C is a scalar in this case. And the sum of U and V is, so the sum of U and V is the vector. Right, so this is the sum vector U plus V equal to U1, U2. Un plus v1, v2 up to vn, right? But basically add the components wise together. So u1 added with v1, u2 added with v2, and so on and so forth up to un added with vn. So you get this is u1 plus v1, comma u2 plus v2 up to un plus vn. Right. So this is vector additions. You can do scalar multiplication as well. So n, this scalar multiple of u, and c is the vector. All right. What you do is you just multiply c with each component of the vector u. Right? So c times u is equal to c u1, comma c u2, comma c un. Right? So that's scalar multiplications of a vector u. All right, so let's perform a few calculations here. So in the next example, you have two vectors or two three-dimensional vectors. So let's do vector additions here. You get 1, comma -3, comma 2 added with 4, comma 2, comma 1, and just add the component wise together. So 1 plus 4 is going to be equal to 5. And then -3 plus 2 is -1, and 2 plus 1 is 3. The next question, you have vector, the difference between two vectors. You have 1, comma -3, comma 2, minus 4, comma 2, comma 1. So 1 minus 4, you have -3. -3 minus 2, you have -5. And 2 minus 1, you have this +1. Okay. In example 6, you have to calculate the representations for vector v because they give you 2 points, initial point 25 and the terminal point 8, 13. So let's do the calculation for v is equal to the first component of the terminal point minus the first component of the initial point. And the second component of the terminal point minus the second component of the initial point, and you get 6, 8 to be vector v. Now do vector additions again. So v plus w, so 6, 8 added with -2, 4. You get the vector 4, 12. The next question is we have some scalar multiplications, the vectors, and then you do the difference between the two vectors. So 3 times v, so 3 times v, 3 times 6, 8, minus 2 times -2, 4. Right, or this is 18, 24 minus -4, 8. Right, you just you do 2 times -2 is -4, and 2 times 4 is 8. And if you do the calculations correctly, you get this is going to be equal to 22, 16. And the last example here, you want to find the component of this vectors. So v minus w. V is equal to 4, 0, 8, minus 6, -1, -4. So 4 minus 6 is -2. 0 minus -1 is +1. And the last component, -8 minus -4 is going to be -4. All right. The next calculations, 6 times u, which is -3, 1, 2, plus 2 times v, which is 4, 0, -8. What you get is -18, 6, 12, plus 8, 0, -16. And you get the vector of the form -10, 6, -4. All right. And the last part here, you have -3 multiplied with this difference. So I'm going to keep -3 throughout the whole calculation. And I'm just going to do this scalar multiple -3 at the end after I find the representation of this difference. So V is equal to 4, 0, -8, minus 8 times 6, comma, -1, comma, -4. Right. So the vectors that you're going to obtain inside the bracket is going to be, if you do the calculations correctly, you get 44, sorry, -44, 8, 24, and now you do the scalar multiple of -3, you get 132, comma, -24, comma, -72. So that is the vectors, additions, vector subtractions, or scalar multiplications on n-dimensional vector. So in this case, we're just going to perform some easy calculations on two-dimensional vectors and three-dimensional vectors. In the next page, we're going to look at different properties of vectors operations. And we're going to revisit this properties later on in lecture 14 when you talk about the vector space. Okay, but for now, we're gonna write down the definitions or write down the properties of the following operations, vectors operations. So let's say you have three vectors in Rn, or n-dimensional vectors, u, v, and w, and you have two real numbers or two scalars, c and d. Here are the properties of the vector operations. And when you talk about operations, you have two operations, vector additions and scalar multiplications. When you perform vector additions, like if you have two n-dimensional vectors, then the sum's also going to be in the n-dimensional as well. Should be the n-dimensional vector as well. So it's u plus v is in Rn, right? You have n-dimensional vector, add with another n-dimensional, the sum's going to be n-dimensional vector, or the vector is in Rn. If that's happened, we call that closure under additions. The next property is the commutative property of additions. You can do the vector addition u plus v, or you can do v plus u. They're going to give you the same answer. So the vector additions are commutative. The next property is the associative properties of additions. Right? If you have three vectors, you want to perform vector additions on the three vectors. You can do u plus v first, and then add with the third vector. Or you can do v plus w first, and then add it with a vector u. Doesn't matter, they're going to give you the same answer as well. The fourth property is additive identity properties. So you have u plus the 0 vector. It's going to give you the original vector back. So in this case, 0 is the identity of vector additions. The next property is additive inverse property. So if you have u plus with negative of u, then you obtain the 0 vector. And number 6, we move on to properties related to scalar multiplications. You have over here in the first properties, you have closure under addition. So two n-dimensional vectors added together, the sum has to be n-dimensional as well. Similar to that, you have closure under scalar multiplications. So a constant multiply with the n-dimensional vectors, then the resulting vector has to be n-dimensional as well. So C times U is in Rn, right? So given U is the n-dimensional vector. there are two different distributive properties. The first one is that if you have C multiplied with U plus V is equal to C times U plus C times V. Right, so this say that you can do vector addition first and then scale the resulting vectors. Or you can scale each vector first and then add them together. Right, so that's the properties. The next property, also the distributive property. Now you have two scale and you apply two scale on a vector. So you have C plus D, apply the scale on vector U. Then either you can scale vector U with C and then scale the vector U with D and then add the resulting vectors together. Number 9 is the associative property of multiplications. So if you have, again, two scales, but you want to multiply these two scales together and then apply the scale on a vector, right? Then you have, so C times D, then later apply the scale on vector U. This is similar to applying one of the scale on U first, so C times D times U. So apply the scale D on U first, and then the resulting vector, you apply another scale C. Or you can apply the scale C first on U. The resulting vectors will get applied to, or you apply another scale on the resulting vector C times U. Now, number 10 is the identity and zero properties of scalar multiplications. So U1 times vector U is going to be vector U itself, and 0 times vector U is going to be 0 vector. So in this case, you say that 1 is the identity of scalar multiplications. Right. And earlier you have 0 is the identity of vector additions. For scalar multiplication, 1 is the identity of scalar multiplications. All right, so moving on to example, right? So in this example, we're going to perform some calculations to find a vector x given the three vectors u, v, and w in R4. So these are the four-dimensional vectors. And from the properties that we got, we know that for vector addition and scalar multiplications, those has to be close for that particular space that you are considering, right? So x has to be a four-dimensional vectors. That's the results. All right, so we're going to quickly perform this calculation. So x is equal to 2 times u, which is 2, negative 1, 5, 0, minus v plus 3 times w. So 4, 3, 1, and negative 1 plus 3 times negative 6, 2, 0, 3. Right. So 2 times this vector, so you scale this vector. Right, so you get 2 times 2 is 4, 2 times negative 1 is negative 2, 2 times 5 is 10, and then 0. And then the vectors inside the parentheses here, you get 4, 3, 1, negative 1 plus negative 18, 6, 0, 9. Then you add these two vectors together. You get the vector of the form negative 14, 9, 1, 10, 8, sorry. And then you do subtractions from one another, or the difference between the two vectors. And you obtain a new vectors of the form 18, right? So 4 minus negative 14 is 18. Negative 2 minus 9 is negative 11. And 10 minus 1 is 9. And the last component, 0 minus 8 is negative 8. All right, so that's problem A. Hopefully, this is the straightforward calculation as well. Moving on to problem B. Now you see that the x value is actually on both sides of the equations. You have x value right here and you have x value right here. Right. So we're gonna do some manipulations on these equations to group value of x or to group x together first. Right. So what you do is first you distribute 3 into the parentheses. So 3x plus 3w equal to 2u minus v plus x. And then what you do is you just move x to the left-hand side and move 3w to the right-hand side. Right. And you get 3x minus x equal to 2u minus v minus 3w. And on the left-hand side, you have 2x equal to 2u. And u is equal to 2 negative 1 5 0 minus v, which is 4 3 1 negative 1 minus 3w, which is negative 6 2 0 and 3. Okay, so I'm going to scale the vector u and scale the vector v. Okay, so the left hand side remains the same at this point. The vector u becomes 4 negative 2 10 0 minus 4 3 1 and negative 1 minus negative 18 minus 6, sorry, plus 6 0 and 9. Right. And then you're gonna do associative property here. So you do this subtraction first, and then the resulting vector will do another subtraction for this vector. So 2x equal to 0, negative 5, 9, 1, minus negative 18, 6, 0, 9, or 2x is equal to 18, negative 11, 9, negative 8. And to get x by itself, we're looking for the representation of the vector x. You divided both sides of the equations for 2. You have x equal to 1/2 times 18, negative 11, 9, negative 8. So basically you scale this resulting vectors, and x is equal to 9, negative 11 over 2, 9 over 2, and negative 4. So that's what you get for this type of calculations using different properties of vector operations. Right? So I didn't write down any operations, properties of operations. It's just very intuitive to perform this kind of calculations. Okay. So moving on to the last part of the lecture, when we talk about briefly, we're going to briefly talk about the concept of linear combinations. And can you get rid of the coordinates as well, please? So just talk about linear combinations. Again, we're going to revisit this type of concept later on in this in the course. All right, linear combinations. So a vector V is a linear combination of vectors v1, v2 up to vn if there exist scalars c1, c2 to cn such that v can be written as c1 times v1 plus c2 times v2 plus up to cn times vn, right? And you say that v is the linear combinations of vectors v1, v2 up to vn. Right? In this case, the c1, the value c1, c2, cn, or c3, c4, and so on and so forth, are called the coefficients of linear combinations. Coefficients of linear combinations. So this is the definitions. Later on in the later lectures, we're going to go back and look at this particular definition, that particular concept, and we're going to perform some calculations so that we can obtain the value of C1, C2, and C, and so on and so forth. All right, so I give you a quick example here. So the following vector, right? So the vector, you have this vector 2, -2, -1. In earlier lectures, we call this a column matrix, but another name that you can use is column vector. You can also have row vectors or row matrix. The name can be used interchangeably. So again, here, this is the column vector. So in this column vector, this particular column vector 2, -2, -1 can be written as a linear combinations of 3 vectors. So you have 3 column vectors, 1, 0, -1, and 2, -3, 1, and 5, -4, 0. Right. So in other words, what you can write is that the vector 2, -2, -1 can be written as linear combinations of these 3 vectors, or this is 3 times 1, 0, -1, plus 2 times 2, -3, +1, and minus 5, -4, 0. And you may wonder, where is 3, 2, -1 coming from? Again, we will go back to this particular concept and learn a technique how to obtain this coefficients, right? But for now, it's just an example that given a vectors and given a vector, you can find other vectors such that this given vector can be written as linear combinations of other vectors. So this is in a way is combinations, and why is linear? Because depends linearly on the vector v1, v2 at the end. All right, so that's it for me in this for this lecture. In this lecture, we look at the vectors, definitions of vectors, and some basic operations to perform on vectors. So we have 2 basic operations: vector addition and scalar multiplication. And we also briefly talk about the linear combinations of vectors. All right, so that's it for me. Please let me know if you have any questions. Thank you.